We close the classical block with a model that's almost pure mathematics. No gradient descent, no boundary to draw, barely any training. It classifies using one of the oldest ideas in probability, plus one wildly simplifying assumption that should ruin it, but somehow doesn't. This is naive Bayes. At its heart is Bayes' theorem, the rule for updating belief with evidence. We want the probability of a class given what we observe. Bayes flips it into things we can actually count from data: how likely the evidence is under each class, times how common that class is to begin with. Belief, updated by evidence. Make it concrete with a spam filter. An email arrives full of words. We want, given these words, what's the probability this is spam? Bayes says combine how likely each word is to appear in spam with how common spam is overall. Words like free and winner push towards spam. Meeting and report push the other way. Here's the bold leap. To make the math easy, naive Bayes assumes every feature is independent of the others, that the word free tells you nothing about whether money also appears. This is almost always false. Words clearly travel together. That's why it's called naive. And yet, the model works remarkably well anyway. With independence, the messy combined probability collapses into something trivial. Just multiply. Take the prior probability of the class, then multiply in the probability of each feature given that class one by one. Do this for every class and pick the winner. A whole classifier reduced to counting and multiplying. Training is barely training, it's just counting. Scan the data once and tally how often each word shows up in spam versus not spam, and how common each class is. That's the entire model. A table of frequencies, no iterations, no optimization. One pass through the data and it's ready to classify. So why does a false assumption give good answers? Because for classification, we don't need the exact probabilities. We only need the right class to come out on top. Even when the independence assumption distorts the actual numbers, it usually distorts them in a way that still ranks the correct class highest. Wrong math, right decision. And it has real strengths. It's blazing fast to train and to predict. It works with very little data, where heavier models would overfit. And it shines on high dimensional text, spam filtering, sentiment, document sorting, where counting words is exactly the right move. For a quick, strong text baseline, it's hard to beat. But watch the traps. The independence assumption means it can't capture how features interact. And there's the zero frequency problem. If a word never appeared in spam during training, its probability is 0. And 1 0 multiplied in wipes out the entire estimate. The fix is smoothing. Pretend every word was seen at least once, so nothing is ever truly impossible. Naive Bayes comes in flavors for different data. Multinomial counts how often things occur. Perfect for word counts in text. Bernoulli tracks simple yes-no presents. And Gaussian handles continuous numbers by assuming each follows a bell curve. Same Bayesian core fitted to the shape of your features. And that completes the classical toolkit: linear and logistic regression, the honest baselines, K nearest neighbors, learning by similarity, support vector machines, the widest margin, trees and random forests, questions and crowds, gradient boosting, fixing mistakes in sequence, K-means, structure without labels, and naive Bayes, pure probability, 7 workhorses that still run the real world. A rough field guide. For most tabular data, start with a random forest or gradient boosting. For text, naive Bayes or a linear model. As an honest baseline, always linear or logistic regression. And reach for deep learning mainly when you have images, audio, language, or truly massive data. Match the tool to the problem. So, naive Bayes wraps up the classics. Count the evidence, apply Bayes, and trust the ranking even when the assumptions are wrong. These 7 algorithms quietly power a huge share of real machine learning. But now, we return to where we started and go deep. Next block, we build the great architectures, the MLP, convolutional networks, recurrent networks, and the transformer. See you there.